Section 11.2 Types of Chemical Reactions. Alright, our third type excuse me, is a single replacement, or sometimes called single displacement reaction. And what happens in a single replacement reaction is one element takes the place of a second element in a compound. So we've got element A plus compound BC. And what happens is element A kicks out element B. You know, it's kind of a bully, and it just takes over. It's like, okay, here's the bully, and here's the boy taking the girl on the date, but the bully is tougher than this boy and kicks it out. And so what happens is we get a new compound, AC, and the boy is all by himself over here. Kind of a sad deal, but this is known as single replacement. What we get in this is both the reactants and the products have an element and a compound. Notice when I wrote it, element, there's just one thing, and there was a compound. I ended up with another compound. Oops, that wasn't quite right. Let's erase that. Let's try that again. I ended up with another compound, AC, and another element. So, element and a compound, element and a compound. That's what you get. That's what you're looking for in single replacement reactions. So anytime a single replacement, that's what you should find. There is one interesting thing, or one kind of confusing thing maybe, about it is you need this, what's called the activity series of metals. It's on page 333. It's also on the back of the periodic tables that I pass out. And it lists elements in order of decreasing reactivity, because in order for one element to take the place of another, it has to be stronger than the one that it's replacing. Here's that chart. So here's what I'm saying. Lithium, it's the tough guy. It can replace anything down below it. Okay? If I look at zinc, he can replace things like iron and lead and hydrogen, but he can't replace the ones above him. Okay, so he can't replace ones above him. And so you look at this chart first to make sure that what you're trying to replace is below what you're starting with. We'll do a couple examples. But first, let's talk about halogens, and they can also replace other halogens, and they go down the chart. So in other words, fluorine, that's the most reactive. It can replace any of them. Then chlorine, then bromine, then iodine. So chlorine, it could replace bromine and iodine, but it couldn't replace fluorine. Not strong enough. All right, let's do this example. So first thing we would do is we'd look on the chart and say, hey, can zinc replace hydrogen? Yeah, it can. So we get some hydrogen left on its own, which would be H2. And then what's our compound? Well, zinc is 2 plus, so, and sulfate is 2 minus, so we get ZnSO4. Now here's halogen. Halogens only replace halogens. Don't stick that one in there. Okay, don't do that. No. Halogens replace halogens. Can chlorine replace bromine? Yeah. So it's going to kick the bromine out. Bromine's left all alone, but bromine's not just single, it's diatomic. And we get the new compound, and you have to put the compound together correctly. Sodium is plus, Cl is minus, NaCl. And then you have to balance. So we would need a 2 here and a 2 there. Okay, so I want you to try these. Make sure that you check the activity chart to make sure that they would replace these. Make sure that iron would replace lead, and so on. So go ahead and do them. Okay, when we do this, we do see that they that iron can do that. So we're going to get lead by itself, and it's just going to be a single element. It's not diatomic or anything. And we're going to get FeNO3 2. Now, you may ask, well, how do I know whether that's going to be, because iron could be 2 plus or 3 plus. I would just simply say that it is usually, if this was a 2 plus, which it is, it would have to be here for it to work with the nitrates, then the iron is, and if the iron can, it's going to be the same thing. They tend to stay the same on these reactions that we're going to do. Alright, on this one, hopefully you notice that we're talking halogens again, so we're replacing these. Remember, chlorine, that's a negative. Negatives wouldn't be listed first. We don't have, negative's not going to take the place of positive, I guess would be a better way of saying it. So the chlorine has to replace the iodine, and it is strong enough to do that. So we're going to be left with iodine by itself. Iodine's diatomic, and we would get NaCl. And now I would need to balance that because it's not perfectly balanced, so I'd put a 2 there and a 2 there. Alright, now this third one might be a little tricky. You're saying, well, what's it going to take the place of? Well, this is a good time to think of this water as that HOH that we've done before. And since calcium is positive, positive ones tend to replace other positive ones. Well, this hydrogen here is going to be positive, because remember, we know that hydroxides are -1. So this is going to be positive. It's going to take the place of that hydrogen. So what we're going to get is, we're going to get some hydrogen. And then we're going to get calcium and hydroxide. Now, calcium is 2 plus. Hydroxide is 1 minus, so it goes together like that, and that's our formula. Okay. Now we would have to go back and balance the equation on this. And if we take a look, we've got 4 hydrogens and 2 oxygens. So if I put a 2 there, that is going to take care of all of that. Okay. Alright, well, we're on to double replacement reactions now. Double replacement is, we've got 2 compounds on the left, and they switch partners. So we have compound AB, compound CD, and what happens is we're going to switch partners. So A is going to go, he's going to dance with D. We get A and D, and he's going to take the place, and C is going to go dance with B. So we've just switched these two. These guys switch partners. They're dancing, they're out dancing, decided to switch partners. That is a double replacement reaction. That's all there is to it. When we're talking about double replacement reactions, they're usually solutions. We're usually talking about things that are aqueous solutions. And they're only going to happen if something is produced like a precipitate, and a precipitate is a substance that doesn't dissolve in water. So when you mix two things together, sometimes you form these substances that no longer dissolve in water, so a reaction takes place, and you notice that right away. A gas, so you mix these two things together, you see these bubbles. Or maybe it just forms water, forms a molecular compound like water. But one of those 3 things needs to happen in order for it to take place. Otherwise, they're just going to float around in the water and nothing's going to happen. They're just going to be there, but no new reaction is going to take place. So, for them to take place, one of the products has to be slightly soluble and form a precipitate. That's what we said. Or you've got to have a gas, or you got to have water. Alright, so let's take a look at a couple examples. If we have calcium bromide and silver nitrate, and we mix those 2 things together. Remember, these are dissolved in water, and I'm not writing the symbols because I don't have enough space on my pad to write all that, but they're there, running around, and they're dissolved in water, and it says, hey, we're going to form this precipitate of silver bromide. So they're telling us that silver bromide, remember now, silver +1, bromine -1, is not soluble, so it's going to be a precipitate. So that tells us that. Well, what else is left? We've used the silver and we've used the bromine. That means we've got calcium and nitrate. So we got to put those together. So calcium, that's a 2 plus. Nitrate is a 1 minus. So we can switch them, and we're going to get CaNO3 2. Now we have to go back and balance the equation. So if we look at calcium's good, Brs, looks like we need 2 of them there. That's going to mess up my silvers, so I'll put 2 there. Now I have 2 nitrates and 2 nitrates, 1 calcium, so it looks like we're good. Alright, on the next one, it says we've got some iron sulfide and hydrochloric acid, and what's formed is a gas. So you put this together, you'd see little bubbles forming, and that gas would be hydrogen sulfide. Wouldn't smell good. Hydrogen sulfide is that rotten egg gas, so wouldn't smell very good. But we know that this is formed, H2S. And what have we got left? Remember, we're talking double replacement reactions, so iron must be taking the place of hydrogen here. And so what's left is iron and chlorine. Well, alright, what's the formula for this? Well, what is the, over here, we know that sulfur is 2 minus, and they're 1 to 1, you know, so the iron must have been 2 plus. So it's going to be 2 plus over here, and going with chlorine, which is 1 minus, cross them, and get Fe2, try that again, how about Fe1, Cl2, okay? Alright, you try these problems. You got sodium hydroxide and iron nitrate, and they're telling you that here's our precipitate, and barium nitrate and phosphoric acid, and they're telling you that barium phosphate is going to be the precipitate. Stop the video, try those. Alright, so let's make iron 3 nitrate. Well, iron 3 hydroxide, Fe OH3. Remember, Fe3 plus hydroxide. If you look it up, 1 minus. So you cross them. So that'd be good. You have what's left. Well, we've got some sodium we haven't used, and we've got some nitrate we haven't used. So we're going to put those together. Sodium is plus 1, nitrate minus 1. So they just go together, 1 to 1, NO3. Okay. So now we have to go back and balance. Sodiums look good. If I go with hydroxides, it looks like I've got 3 over here and 1 here. So I better put a 3, which of course messed up my sodiums. So I better put a 3 there. Now looking at irons, yeah. 3 nitrates here. Remember, NO3, I'm counting that as one thing, and I've got 3 more of those. So 3 nitrates here. So that's good. So I'm balanced. Alright, in the next one, it says barium phosphate is a precipitate. So barium's 2 plus, phosphate, PO4, 3 minus. Well, we're going to do a little crisscrossing stuff. Looks like we're going to get a compound called formula Ba3 PO4 2 plus, well, what's left? We've got some nitrates we haven't used, and we've got some hydrogen. Okay, so we'll put that together. Hydrogen plus nitrate. Hydrogen is plus 1, nitrate minus 1. Looks like HNO3. So, must get some nitric acid there. Alright, let's balance this now. Let's see how we do. We got a 3 for barium, so we're going to put a 3 out front. Now, if you look at that, it gives me 3 times 2 of the NO3s. So that's 6. Alright, so we'll go 6 there. We could do hydrogens. We've got a 3 here and a 6 of them over here. We need twice that many. Put a 2 there. And phosphates, there's phosphate, 2 phosphates. And looks like 2 phosphates over here. So looks like we're good. 3, 2, 1, 6 for our final answer there.